Just want to double check, make sure. Of course, my microphone needs to be on. There we go. So we've got microphone going. I'll just get a double check with everyone before we go live. I'll give it a couple of minutes just to get everyone in here. We are live. I'm going to double check on that. Here we go. Double check on that. Double check on this. Here we go. YouTube. All right. Okay. There we go. We're live there. Let's see if we could hear anything. Oh, good, good, good. We can hear me. That's great. Fantastic. I'm hoping Twitch is good too. Hello from Germany. Hello, Andreas. Here we go. Fantastic. Okay. Well, I better get started then. All right. Greetings, interwebs. It is I, Hewlett, David Hewlett, and I am again the luckiest man alive because I get to talk today with Oliver Jennrich. If I'm saying that right, I'm sure I will be corrected later if I'm not. Oliver is the man to talk to about basically any aspect of what ESA is doing in space, but particularly with these gravitational waves. So I'm going to invite him to the Zoom now. Here we go. I will now turn on audio for you as well. There we go. And I guess I'm going to readjust my little screen. Let's see. All right. Why am I not hearing him? Here we go. There we go. How's that? Hello, Oliver.
Hi, David. Good to be here.
Thank you so much for this. I have had so much fun doing my research for this because you've just got, I mean, you've done everything from teaching astronauts cosmology to basically listening to the earliest, or largest universal or galaxy-wide stellar events. I mean, you got some amazing stuff going on. Could you explain to people, who you are and what you do?
Yeah. So thank you for having me. It's an honor, right? So yeah, I'm a scientist working at the European Space Agency, and usually saying NASA, that's something like ESA just for the US. So we are the European Space Agency, roughly comparable to NASA, just, a little bit smaller and probably slightly lower profile. My job here at the agency is I'm one of the project scientists for a gravitational wave detector in space, LISA, that we just have started to construct. So you said I'm listening to the echo of faraway galaxies. Not yet. I hope to in the not too far future, but we are building the instruments there. My background is I'm a physicist. I'm not an astronomer. And I essentially spent my scientist life in the business of building gravitational wave detectors, either on ground or in space, or to put it more precisely, I was a tiny little cog in the big machinery that built those fantastic detectors. And I'm also a small, tiny little cog here in the vast team that will build the space detector.
So for people who aren't familiar with this stuff, like myself, gravitational waves and gravitational wave detectors, these are these massive things that you've built on the surface of the Earth in order to detect gravitational waves, and then you're now moving into space. But what exactly is a gravitational wave for people who don't understand that?
Yeah, it's a little bit difficult to imagine that because normally we are not talking about the fabric of space-time because we just usually take it for granted that there is space around it and time,
right.
And
like
then there's some people might. Like fish and water, exactly. Yeah. You wouldn't notice, or even the atmosphere. You're breathing every day, but you're not noticing it. So, in essence, what gravitational waves are is probably best described by what they're doing. And gravitational waves change distances. That's all there is, right? So they modify space-time such that the distance between 2 points changes slightly. And they are waves because they propagate like waves. They have the same equations like waves. So if you look at the waves we normally talk about, where everybody is familiar with, certainly everybody who listens to your podcast, that light is a wave, right? An electromagnetic wave. And gravitational waves are the same manifestation of this wave thingy in space-time. And you have that, if you can see that behind me, the ripples in space-time, you see the two black holes in the center. I think the thing that's most difficult to wrap your mind around in gravitational waves is not so much that they change distances. I mean, we know everyday experience that things change distances, right? That's not a big thing. The thing is that the distance changes that we are measuring are very, very small. And you need enormous masses to create them. So we are talking about black holes of at least 10, 20 solar masses that spiral in, merge, and then, ring down and send out the signals so that we can detect them on ground. For space, we are talking about things that have 10 to the 5, so 100,000 solar masses. And yet, for space, if we're talking about space, we are changing the distance of two objects that are 2.5 million kilometers apart, like our satellites, by picometers. So just a reminder, a millionth of a thousandth of a millimeter is the micrometer, then a millionth of a millimeter is a nanometer. And then I'm getting into trouble with different sides of the Atlantic. The next power of 3. So, the American billionth of a millimeter is a picometer.
But that seems like almost like a rounding error. Like, how do you know you got something? I mean,
well, you have a very, very careful measurement. No, I mean, I'm joking. But the thing is that, of course, you have to make sure that your detector is sensitive enough. That's one thing. But, to measure picometers, it sounds almost a bit blasé, but that's not the difficult part. I mean, if you have your standard physics student in the lab, or pretty much everybody in the lab, it's not very difficult to measure length changes of picometers because we have a very, very sensitive measurement device. This is laser interferometry, where we use the wavelength of a laser as a scale, and then we watch how the distance changes. That's, I would say, the easy part. The difficult part is to make sure that the distance changes you're measuring have something to do with these guys there. Right? I mean, everything rattles
not
around.
Some interference that's happening in your lab.
It's like if I challenge you to measure the distance between, let's say, Chicago and LA to a hundredth of a millimeter, for example, then you start wondering how much do the endpoints of my measurement change? Is the measurement thing that I use, the yardstick, your bend measure thing, is that expanding or contracting? Is it elastic? Is it, does it go through different temperature zones? Does it matter if the sun comes up or not? So you see, this is making sense is the difficult part. And,
but what about doing it in space has got to be part of the hard part too, though, isn't it? I mean, that you're going to be doing that same thing, but in space.
Space is always. I mean, the saying is, particularly when things go wrong, space is hard. And yes, space is hard. The hardest part, there are a couple of things in space that are really hard, which has to do with the space environment. Right, you're in vacuum. You are under illumination from the sun, which on the one side usually brings you power, on the other side it has hard X-rays, it has protons, it has all the stuff that you don't like, and which normally our atmosphere takes care of. The other part that's hard in space is that typically you don't have people there who can go and fix things. Right? I mean, you all know that sometimes if you build a halfway complex machinery, something gets stuck and all you need to go and, you slap it a bit and then it works again. Right? And you can't do that. And unless you're on the space station, but the space station has other problems, right? The problem is that there are humans around and everything rattles. So you need to automate things. You need to make things robust so that they survive the kind of nasty environment in space.
Yeah. And
Once you're beyond that, things become easy because there's a lot of stuff in space that's not happening in space, but that happens on ground that disturbs our measurement, which is the reason why we go there. Not because we like it so much, but because it's actually giving us a much better environment. Well, no people, no traffic,
Right.
no seismic of the Earth, no weather patterns, no atmosphere, all the stuff that is, or for example, if you look at the ground-based detectors, the one particularly in Louisiana and Baton Rouge, no alligators. That's a big plus.
is it?
Right?
Yeah, no kidding. But it's funny. One of the great little pieces that you talked about in your TED talk, which just caught I don't know why it got my fancy, was the fact that you were saying that you've got to be flatter than flat. Like basically, maybe we should explain exactly how this works. So exactly how you're measuring these things. But the idea that you're using a laser, so you can't, and if it's a laser over a long period of time, there's a curve to the Earth.
Yeah.
So you actually have to dig into the Earth to have a flatter than flat setting for these things.
If you do that on ground, so and the principle that we employ is the same one, just on ground, it's a little bit easier to put the mirrors in place. You send a laser beam from the beam. You send a laser beam out. You have it hit a beam splitter that sends the laser, let's say, one part of the laser to the left and the other one straight ahead. And then at the end of a certain set distance, let's say for LIGO 4 kilometers, you have a mirror that reflects the light back. And in principle, it's sent a couple of times back and forth, but that's a technical detail. The laser recombines on the beam splitter and gives you the interference pattern. Because on one arm, it takes a certain time, and the other arm it takes a slightly different time. And so, the phase relationship of the light coming back is some number. So you see either, wave trough on wave trough, which is the one side of positive interference, or you have trough on crest, where you have the other way around, right? Trough on crest, or well, never mind. So
it's either making it stronger
the
or
one
weaker.
or the other, where the light disappears, right? Which we call the destructive interference, and we are just looking not into the interference pattern. We are looking at the change of the interference pattern when the gravitational wave passes through. But if you send a laser light 4 kilometers on the surface of the Earth, believe it or not, the Earth is a sphere, right? So with a certain radius.
And some people don't believe it.
Some people don't believe it, and I challenge them. I mean, it's a weird feeling, even on. I never had the chance to visit the LIGO site during the construction. But I was very much involved in the prototype that we had in Germany, where it's only 600 meters. But already on 600 meters, you get a feeling for the thing that it is really flat. It is really flat, and you don't see the curvature. It's not, but it is a different feeling from normal flat, right? Which is like on the sea where you have the horizon, but at the end, the ocean, the sea is part of a sphere, right? Your laser light doesn't care about gravity that much. It just goes straight. And therefore, you have to actually, if you transform that back to the surface of the Earth, then you effectively have to correct for the curvature of the Earth so that the tunnel you shoot the light through is actually straight. Right? Yeah. And that's an interesting demonstration of the Earth as a sphere.
Yeah, it really caught my imagination for some reason. That aspect of it, where just like that you just don't think of it. You don't think of it in such. I mean, that feels like a very short space to be able to notice.
And this is one of those classical things where you're right. I never thought about that. Yeah, but of course, if you calculate it, sure, right? It has to be, and it's it is visible on 4 kilometers length. So it's not really visible on much shorter length, but still it tells you there's something with your local surface that's not the way, it's not flat as you think of it. I mean, not even here in the Netherlands, right, where we have a lot of flatness,
right.
An abundance of it even. And but it's a different kind of flatness indeed.
So, and by looking and seeing how these interference patterns work with the lasers. It's exactly the same things happening in space. That's the same. I mean, other than the obvious.
It is in principle. So what I said, just described in for LIGO and also the Virgo colleagues, is a classical Michelson interferometer, right? You split up the light in two directions. Doesn't have to be 90 degrees. It's just practical. You split it up in two directions. You send it out. You reflect it back, and you recombine.
Right.
And you can do that if you have a handful of kilometers. But if you go like Lisa for 2.5 million kilometers, you see light. The light beams, even laser beams, are not perfectly straight. They have what we call divergence. That has to do with refraction of the light. Light is a wave, so therefore it expands over distance, right? So the laser beam becomes bigger. Normally you wouldn't notice that. On that distances, you do notice it. So we sent out a laser beam that's about 30 kilometers wide, 30 meters wide, because that's the diameter of our telescope.
Wow.
2.5 million kilometers later, it is kilometers in width.
Wow.
Right? So, but the other telescope, we cannot build 30-kilometer telescopes in space. We can't do that on ground either. So on the other side, we have a 30-centimeter telescope as well. So it takes out a tiny little bit of that light of this vast laser beam. And it's about, something like a tenth of a billionth of the total power of the light is collected. About.
Really?
That, right? So if you want to reflect that back, right, you go through this factor twice. And that means that, you're barely any light left when you do that. So we have to employ a little trick there, which is quite common in any space mission, but normally we play that trick on the radio frequencies that we use to communicate with the spacecraft, which is what we call a transponder lock. There is an amplifier on board, a receiver and an amplifier on board that receives the light, measures the phase of it, and sends out a laser with exactly the same phase relationship. So we effectively use the little light that comes, boost it up again, but with a fixed phase relation, not just like your audio amplifier, just crank it up and, just amplify the power, but also the making sure that it's exactly the right phase again. And then we send it back. So that is the tiny little trick that we don't use a mirror, because we can't build mirrors that are big enough to send back actually a useful amount of light.
Right.
Light, yes, but not useful.
Right. So it would just that expansion would just continue, and it would be useless by the time you get there.
Exactly. So you're effectively going through this whole step where you only take out a tiny bit of light out of this vastly widened up laser beam, and you do that twice. And of course, these kind of factors multiply. So at the end, you're left with a handful of photons or something like that, which are there but not useful, right?
So. Okay, so we figured out how to do this, but what are we what are we listening to? What is the difference between the stuff on Earth? We've been able to hear. It was a supernova, was it not, or what was it? There was
no, it was. Sadly, no, it was never a supernova. That's the interesting part. So those machines were originally aimed at detecting supernova. I don't think we have seen a single one. We've seen the coalescence of objects like stellar-sized black holes, and with stellar size, a little bit of a hand waving here. So we typically talk about 10 to 50 solar masses, so the mass of the sun.
Right.
And this is what we call stellar-sized black holes, because we know that there are stars out there, plenty of them, that have roughly that mass.
And they have to be that big for you to detect them. They've got to be incredibly huge in order to detect them on your small little.
This is the thing. They have to have that mass to emit enough gravitational waves, called gravitational waves, with enough strength, amplitude, so that we on Earth can detect it.
Right, yeah, okay.
But they also happen to have, if they are emitting if they are that size, they are also emitting at a characteristic frequency that has effectively to do with the size of these things. Right. Because if you see this thing there in the background, you see the two black holes, right? And there's no scale. It doesn't tell you if these are solar mass black holes or if they are 10 to the 6 solar masses. But it really doesn't matter. What you see is that they have kind of a characteristic size, which we call the event horizon of black holes, and they have a mass, and they orbit each other. And now if you have something that is 10 to the 5 solar masses, you can imagine that it takes a little bit longer for them to go around because they're much heavier. Right? So they are not exactly swift. Whereas the smaller they are, the quicker they go around. Now, having said that, the quicker they complete one orbit, because I'm sure some of your listeners will immediately correct me and tell me, hang on a second, don't fall all masses with the same rate, and shouldn't they fall with exactly the same speed? Yes, they do. Briefly before coalescence, about 60% of the speed of light. So there are objects out there that weigh 10 to the 6 solar masses, have a mass of 10 to the 6 solar masses, and move around with 10 to the 6 with 60% of the speed of light.
Wow.
That's frightening, right?
Yeah.
All of them do. It's just that they are so much bigger, and the orbit is so much bigger that they take longer to go around. Long story short, the bigger the object, the lower the frequency. So the ground-based colleagues, the detectors, have what we call audio frequency, so up to 100 hertz or something like that, maybe from 10 hertz. It is a little bit on the bass side of audio frequencies, right?
Right. We can it's all about the bass.
Here up to kilohertz, but depending on your age and your musical history. But the exactly, but the things that we are we are looking for have not tens of solar masses, but hundreds, thousands of solar masses. Yeah. So there is an intrinsic factor 10 to the 5, 100,000 also in frequency. So where ground-based detectors see things at, let's say, 10 hertz, 100 hertz, right? We are seeing things at 10 to the minus 4 hertz to maybe a millihertz. So we are much lower in frequency. And that is also the reason why we need to go to space, because millihertz, if you do the quick mental calculation, that's 1,000 seconds. So among friends, a time scale of an hour, right? It's very difficult to keep things stable on timescales of an hour.
Yeah.
The sun goes up, the sun goes down. Okay, that's maybe 10 hours. The rain comes, rain goes, right? That's maybe also timescales of hours. The temperature of your building goes up and down. People come to work, people leave. And
humidity
so it's very... Humidity changes. I mean, you can come up with a ton of effects very easily that convinces you that it is very, very difficult to create a detector on ground that has any meaningful sensitivity much below a hertz. You can push, and the colleagues do, and they are doing fantastic technologies, but going on ground to much below 1 hertz, and with much below 1 hertz, I mean like a factor 1,000 or so, not just a factor 2, it's impossible and with current technology. So this is why we go to space, because there we get rid of all this noise that, life and a planet provides us with.
And we can listen to frequencies that would have been interfered with by what's going on here, basically.
Yeah. Exactly. So we have frequencies that interfere, much, much lower, because we're going around the sun in sync with the Earth. So we are slightly behind the Earth. So, and of course, the Earth attracts us. The moon goes around, right? But the moon has frequencies of 1 over a month. That's not 10 to the minus 6 hertz among friends, right? And Jupiter,
you're getting that, so you can say,
exactly. You can see that, and you say, yeah, that's not for me, right? I'm looking at that band, and then the question is, what can we see with that, right? Are there sources out there? And we currently believe that pretty much every self-respecting galaxy has a black hole in the center.
All the cool galaxies have a black hole, right?
All the cool galaxies have one. There are a couple of them that are a bit fishy, that look like a little bit dull, but most of the galaxies have a black hole in the center. And the question is, how did it get there? Right? It's a kind of a cosmic chicken and egg problem, where the black hole's there, and the stars formed around the black holes because the gas fell in and compacted and started to build stars, or were the stars first, and then a couple of them sank to the center and became black holes, and then the black holes merged and emitted gravitational waves, and then more things came in and emitted gravitational waves. Whereas if the black holes were first, then we probably only see the merger of black holes when galaxies merge. So the kind of signals, how often we see signals, and how big the sources are, and with big, I mean literally the mass or the diameter, it's the same in that regime, tells us, can tell us very, very well how the early galaxies in the universe formed. And with early galaxies, I mean really the first one, not something later. I mean the first time galaxies ever appeared on a cosmic timescale, when they merge, or if the black hole in the center starts feeding on other black holes, we'll see it.
So you could basically answer that, potentially you could answer that question about whether it's black holes or, wow.
Yeah, and this is funny, right? Because if you interview me in 10, 15 years again, right, and you remind me, Oliver, you said you can potentially distinguish between those things. Yeah, I probably have to say, this is what we thought at the time, right? When we switched that thing on, we realized there are so many things out there that we don't understand.
Yeah.
Our detector works, it works perfectly, but we see things we never imagined that are out there. And that, we figured that out, but really that was the boring part. The interesting part is this thing that nobody thought about. This strange phenomenon that nobody had on his bingo list, right? I mean, it happens all the time.
Well, and that was, again, it was something that the way you ended your TED Talk, which I suggest everyone listen to, because it's wonderful. I mean, it's not aimed at kids, but it's aimed at sort of that wonder. It
was in a framework of a local high school here that it did that. So I toned it. I aimed it at people who have not necessarily a physics PhD.
But what was great about it, I mean, other than obviously just all the fabulous science, was just this feeling of like, oh my God, like what are we gonna find? Like that's the thing that I find so exciting about this stuff. Is you go
this is we had for a while, we went around and sold that mission with ESA opens a new window to the universe. Now, if you use advertising slogans too often, they become stale, so we don't use that anymore. But it is literally like that, right? It is a part of our tool set in astronomy that we never used before. So it's like you imagine, and there's probably online versions of talks from Bernhard Schutz, one of our senior members of the LISA collaboration, who usually showed a picture or a movie short clip of a jungle scene, right, where you have this wonderful trees and colors and all that, but it was just silent. It was beautiful. And then at some point he switched on the sound, and you heard the birds, and you heard the tiger roaring in the background, right? And all of a sudden you realize how much information you were missing till that point, because you switched on a new channel. It is not like, I switch on. I mean, even with X-rays, when the first time with Rosat, when we had the first X-ray satellite in orbit, you can't observe, I mean, probably many people know that, but X-rays you can only do from orbit because the atmosphere absorbs them. You can't do X-ray astronomy from the ground. So we never knew that was something up there. The first thing you go up there and you see, oh shit, the sky is alight with X-ray sources. Where are they coming from, right? And so this is the same thing, right? You switch on a new detector and you all of a sudden see there's a whole new world out there, a whole new universe. It's not a new one, it's the same one. It's just you all of a sudden see things that you haven't seen before. And even those big masses there, this 10 to this 6 solar mass black holes, they are kind of predictable these days, but the sources that LIGO saw, the 10 to the 10, 20, 30 solar masses, right? That was, of course, there's always speculation that these things existed, but there was no clear evidence. I mean, so, they might be there. And then LIGO sees literally hundreds of them by now.
Right.
And so you start wondering, we missed a big part of the universe.
A huge
and,
part.
Yeah, exactly, and a heavy part of that. I mean, there are even people who seriously speculate about maybe we missed so many black holes of that size, which are very difficult to see in any other way.
Yeah.
Normally, black holes you can detect by the fact that they also deflect light, right?
Yeah, of course.
So you effectively see them by their shadow, quote unquote.
Right.
But with the wee ones, they're difficult to see. They are not big enough to actually, but you have a high enough probability to see them in your telescope. But if there are enough of them, they could make up for a substantial fraction of dark matter, which is one of those other things that we don't know, right? Which is a big mystery. Now, is that true? We don't know. I mean, we don't have enough data yet. It could be, which would then answer, well, we now know, I don't know what, 50% of what makes up dark matter and what's the other 50%. We still have no clue. But again, this is something like, you look at new things and you have a new detector and you switch things on, and typically the first thing you see surprises you once the detector is working.
Yeah.
Typically it takes a while to make this thing work, but once they work, you see things that you say, oh, where's that coming from? I've never seen that before. Yeah, you never had a detector like that. Of course you didn't see it before, right?
Yeah. It is amazing. I mean, how will we quote unquote see these things? Like, how do you present these findings? Is it, I've heard chirps. I've seen graphs. I mean, how do you illustrate this stuff?
Sadly, with difficulties, right? I mean, this is something that with colleagues we thought about that for a while in how to actually present things, but because let's not ignore, I mean, the fact that pictures from the Hubble Space Telescope played a huge role in keeping that thing alive and also get funding for bigger telescopes.
Well, look at James Webb. The stuff coming out of that.
Everybody looks at fantastic James Webb pictures, right? I mean, even from the telescope size, quite small mission Euclid, which only has a meter of the diameter of the telescope, but with fantastic quality. People were all over us about the early release observations because they were unprecedented detail in with a wide field of view. So it's one of those fantastic things that you can zoom in and in and in and in and in and in. And this is what captures the people. We are visual animals, right? Now with gravitational waves, they are very hard to visualize, not because we are not creative enough, and yes, that might play a role, but the thing is, if you are looking at optical telescopes, their accuracy with which they can determine where the light is coming from is very, 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 very good, depending on the telescope, obviously. But, a 60th of a degree is not even a challenge, right? It's an arc second, which is already, an enormous number in astronomy. But for LISA, particularly for LISA and also for the ground-based detectors, because we are using so low frequencies, our detectors are simply not big enough to have a nice, shiny picture of the universe where you say, there's a point, the gravitational waves come from there. So if you remember maybe having seen, you said you heard the chirp, maybe you have seen all sky plots of the probability, and it's somewhere over there, right?
Yeah.
And because they can't do it better, right?
It's like early audio recordings. Early audio recordings, you get the sense, but you don't get the...
I mean, it's our ears are a good example. I mean, our ears are what, 30 centimeters apart, depending on something like 20 or whatever, right? Depending on the size of your head. But that's in audio frequencies, it's a kilohertz, right? So then you go and say, well, I can probably pinpoint the source of a kilohertz beep relatively good, maybe on a 5 kilohertz even better, right? I can turn my head and say it's over there. Well, try that with a 50 hertz hum, or for the transatlantic listeners, 60 hertz, your base frequency of your power grid, right? Which you have everywhere in your lab if you switch on an instrument. And the hum is everywhere because the wavelength is so big that it doesn't make any difference which direction you face. You always hear the same hum, right? And we are a little bit in this problem with LISA, that we are detecting things that are millihertz, so 1,000 seconds, right? Now, some of you might know that the Earth's distance to the Sun is also about 500 seconds. So the diameter of the Earth orbit, which is also the LISA orbit, is 1,000 seconds. So you just built a telescope with a little bit of hand waving. You just built yourself a telescope where your main mirror, your main signal collecting thingy, is about the size of a wavelength. Right? Whereas if you go to VLT or one of those big guys out there with 8-meter wavelengths, right? With 8-meter diameter, then you are easily on the level of 10 million wavelengths diameter of the telescope. So, which is why we can't really do much in terms of pinpointing the thing. We are usually saying if we get things to the size, you know, the uncertainty on the sky, we can say it's coming from there to the size of the full moon on the sky. We are golden. It's that bad. Or on the other hand, it's that good, right? I mean, you depending on how you play it, obviously, but it's not where we can play, where we can, you know, Horsehead Nebula and gravitational waves. That's a blob. Right? I mean, that's a uniformly colored picture because the probability doesn't change on those times, on those length scales.
So you just know that there's something there, but not you just can't get
as I said, we try to keep it, the loud ones, we like to keep it to within the size of the moon, which is
it reminds me
also quite nice with others.
It reminds me of an issue that entomologists had with crickets and the little mites that were attacking the crickets, and they couldn't figure out how these tiny little mites were hearing these crickets because the wavelengths were too big for them to be hearing, and so there's this whole sort of like search to figure out how this stuff works.
It is a little bit like that, right? Only that it turns out that it doesn't. I mean, you know that from you are roughly my age, so you remember antennas and radios, right? It's not all streamed over the internet. So, but you know, your typical AM frequency is 100 kilohertz, 800 kilohertz, something like that, right? And your VHF is a couple of hundred megahertz. But even a couple of hundred megahertz is still 30 meters or so in terms of wavelength. Your antenna was not even close to that. It had, you know, was that, you know, the little rabbit ears, right? That long. So we know that we can detect signals with antennas that are much smaller than this wavelength of the signal. What we can't do very well is to figure out the direction where it's coming from.
Yeah, of course.
Right. So, and this is kind of a second order problem. Detecting things is one thing. We know we can do that with this size of detectors. Figuring out precisely where they're coming from is more difficult, which is where the dimension of your detector comes into play.
Is that because we just don't have sensitive enough equipment to do that? I mean, is it possible that on one of those, like to use the antenna example, is it possible that we could tell that this is coming in slightly faster?
Sure. It is always, you know, hand-waving things. Our detector is the size of the wavelength, and therefore we can't be too precise. It's all a question about what we typically call signal to noise. How big is the signal compared to the noise of our detector? If you have an extremely loud detector signal, if you have an extremely bright light, it's very strong radio emitter, you can do it much better as if your thing is just above the noise where you don't know what's going on. So that plays a role. And, you know, the noise level of our detectors, that's driven by technology, mostly.
And where's the innovation? Where's the innovation on that stuff? Where's it going? Is it quantum? I'm assuming it's got to be quantum physics related of some sort. Seems to be the answer.
It's difficult because, well, you could say that. I mean, we can also say probably AI or blockchain. No, seriously. The innovation that would be necessary is, I mean, we are limited with probably all detectors. Well, certainly space-based detectors at the moment. We are limited by the part which I said is the difficult part, is making sense of the signal, where we say, is this signal coming from a gravitational wave, or is that some other stuff that changes the distance between our spacecraft? And these are classical forces. I mean, you have your test mass inside your satellite, right? And we will have the satellite as a heavy test mass, about 2 kilograms, and we try to make sure that nothing else but gravity determines the position of that test mass. But it has limits, right? The satellite inside it's not in vacuum. It's theoretically a vacuum because we are in interplanetary space, but we are close to materials in the satellite that emit gas, right? I mean, typically hydrogen and nitrogen. So, you have this residual gas molecules that hit your test mass and shift it slightly one direction. And we are that sensitive. We see on ESA Pathfinder, the technological precursor, we saw effectively the effect of air molecules or gas molecules still hitting the test mass.
Really?
So it is quantum is not necessarily the answer. It's potentially the answer in a very weird way, because if you go for what people they use the condensed atoms, so Bose-Einstein condensates.
We're talking to Lisa
exactly.
Werner
Then
about that.
Exactly. Lisa is a good person to talk to
Fantastic.
about that. And if you use those as reference points, you have one big technology step to overcome, which is that the Bose-Einstein condensates have about, I don't know where the limit is at the moment, but I guess about a million, maybe 10 million atoms or something like that. A lump of matter of any reasonable size has roughly the Avogadro number in there, which is 10 to the 23. Right? So there are immediately 17 orders of magnitude where you need much more mass in there to be as insensitive to stray forces. However, if you had that, you have this weird and wonderful effect that if an atom in the BEC is disturbed, right, a part of the BEC is disturbed, that it leaves the collective. So it doesn't play with you anymore. So if you manage to hook your lasers on that laser onto the as a reference to your BEC and say, well, I'm measuring the position of that one, then effectively you're insensitive to the stuff that's kicked out and is rattling around. So, but yeah, you're still quite a bit away to have the same sensitivity that we have with microscopic test masses, but future might lie there. Or the future might be in different detecting technologies. At the moment, we are just very, very basic, measuring the distance of the change of distance between 2 points, right? And there are plenty of people who are talking about maybe the other ways of detecting gravitational waves.
What other things are out there? What other kinds of technologies are they considering?
You could talk about polarization change of lasers, probably. You could talk about a proposed coupling between gravitational waves and magnetic fields. But to exploit that, you typically need enormous amount of electromagnetic field strength. So in other words, big lasers. And very big lasers. Really big lasers. And,
how big? How big a laser?
I don't know where the current estimates are, but I would guess you're talking about something fusion class lasers.
Oh wow! Okay, right. All right.
So, which is where we are not even close to get up to space. I mean, we are not even close to have them operating continuously on ground. They are just pulse things. But
so these are the ones that are contained by magnetic, incredibly strong magnetic fields, right?
I mean, that's really the realm of science fiction, right? If you think maybe we could do that in the future, then you're projecting your way far into the future. At the moment, the best thing we can do by far is to measure the distance, and there really the distance measurement is not really the problem. It's challenging, and particularly for the ground-based colleagues, it's extremely challenging because also you need to look into very, very weird effects of materials there. But for us, the critical thing is to make sure that we know that the distance change has been created by a gravitational wave.
And what inspired you into this stuff? I mean, what got you excited about this in the first place? I mean,
this is an interesting question, right? I mean, you have these people who tell you, I always wanted to be an astronaut when I was a kid. Well, I had no interest. I'm afraid of heights. But the thing is, well, I studied physics, right? And then the question is, what do I do for a diploma thesis or the American equivalent of a master's? And I say, we had a professor there who worked on very advanced concepts of the standard model of particle physics. So it was effectively high energy physics. And he had as a hobby, so he wanted to understand gravitational wave detectors. I said, okay, you do some calculations. And I did some calculations. And then when I handed in my thesis, I thought, now what? And then there was, we have a new professor. He's wanting to build a prototype for a ground-based gravitational wave detector. He's looking for PhD students. And I said, okay, cool, right? And then I went there and he said, effectively within 10 minutes, yeah, you can start. I thought, I have no clue. Don't you worry, he will teach you what you need to do. Well, yes, he did. It took a bit longer than usual, but it was an intense time, very interesting time. And then, from the ground-based community, the ground-based in the space-based community, certainly in the early days, and we are talking here mid-90s, right?
Okay.
Was pretty much identical. It was driven by experimentalists with people who had a clue how to build things. And so it was always a lively exchange. So you worked on the ground-based detectors, then you worked for a while on space-based detectors and back again. So this is how I had my first postdoc in the US and working on LISA. I had a student already in Germany who was working on aspects of LISA, so I was interested. And then eventually there was the opportunity to work with the European Space Agency on that detector. And I said, well, I just apply. And apparently I was, good enough to be employed. But what really got me, I mean, it's really one of those things you grow into. It's not like, there are gravitational waves. I always wanted to gravitational waves.
Right.
It's
As a child.
that grew on the way. No, as a child, I never knew about that. Right. Yeah. And gravitational waves, to be honest, were never a big thing until the early 90s, when the first big proposals for the big detectors like LIGO and so on came into play. And before that, it was a niche thing.
And didn't Einstein think it was impossible to detect them anyways? Like he predicted them,
he had that. I mean, we were talking about when we warmed up a bit about this book, Gravity's Century. The history is a little bit laid out, and he seemed to have flip-flopped about the idea, it's detectable, it's not detectable. And it was also one of these things that he didn't get it right with the first shot, right? So he published a paper, and then he published another paper saying, I have to address an unfortunate mathematical error. Right. It happens to the best, apparently. But the problem is they are weak, right? We are talking about things here that require neutron star-sized masses, stellar-sized masses, moving around to create something that changes the distance on the Earth at 10 to the minus 18 meters, right? If you think back, we can't think back because none of us was alive at that time, but we know what Einstein knew about the universe because we knew what the rest of humankind knew about the universe.
Right.
The universe was our galaxy. It was not clear that there are other galaxies in the universe.
Yeah, it's weird.
And that came with Edwin Hubble and the namesake of the Hubble constant. He discovered that certain objects, nebula, were looking as if they are moving away from the Milky Way and are also way too far away from us to actually be in the Milky Way.
Right.
So all of a sudden the universe opened up and say, there's more than one galaxy. And then all these things came together, and then people started to hypothesize about neutron stars. They started to hypothesize about black holes. And then, all those astronomical objects that we these days take simply for granted, Einstein didn't know that they exist. So, I think it's understandable that he didn't quite believe that you will ever be able to detect it.
Yeah.
Right?
Yeah.
Not that they are not there, but that the effect is so tiny that, and it is, if you just wave your hand around and say, what's the gravitational wave emission of me doing that? Well, yes, you can calculate that, but you end up with awfully large negative numbers in the exponents of your of your values, right? And it's not detectable. So you need those big boys and girls that do the dance and then emit things, right? And
Right.
Einstein wasn't aware that they exist.
It is extraordinary to think how we've changed our perspective on this.
Yeah.
There was an amazing book I remember
Indeed.
reading years ago, a Timothy Ferris book called "Coming of Age Under the Milky Way," and
Yeah.
it was a history, but it was a history of our changing perspective of the skies,
Yeah.
and it was just wonderful just to see how
Yeah.
we just kept the model kept changing, and then just basically got bigger and bigger and bigger.
And it's not only, also we take that for granted, and so do I certainly. I mean, we know the Milky Way has a certain diameter, and the next galaxy is so many light years away, and then, we are in a cluster, and then, the universe is 13.9 billion years old, and blah, 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 blah. But how did you come to that one? You need to measure distances precisely enough.
Right.
You need to figure out how to measure distances to the next star. You can't go there with your yardstick, right? So you have to do other methods. You do trigonometry, you do astrometry. You find out, you look at the star now and half a year later, and you see how it moves across the sky, right, against the far away background. This is this parallax method. That only works in our Milky Way, right? If you go further away, you can't do that because the changes are too small. So you're looking into other things about stars where you know the intrinsic brightness very well. And then you go with the 1/r² law and say, if I see that much light and I know it should have emitted that much, it must be that far away.
Right.
And that also works for a while. And then you get into this whole argument about Hubble's constant, where you say the further away they are, the faster they move away. Why don't I take the velocity as a measure for the distance? And this is what we do these days, right? This is how we discovered, this is how people discovered that the universe is expanding, that the expansion of the universe is accelerating even. Right?
Something else that we discovered within our lifetime, or certainly within another crazy stuff.
So there are a couple of key things that I remember. I wasn't the most, what you would call, observant student. Well, I went to talks, but easily distracted and all that. But I remember two things vividly. Where we had a talk from a guy who was looking into solar neutrinos.
Right.
And at that point, it was a big problem that there were too few neutrinos emitted from the sun.
Right.
To the point where some people started speculating maybe the sun has gone out, maybe the nuclear fusion stopped at the center of the sun. We would only notice that a million years later because it takes a while for the photons to get out. But the neutrinos, you would see them immediately. But the solution for that one was that neutrinos have mass, and therefore oscillate between different kind of neutrinos, and our detectors can only detect one of those kinds. So if you were just in a, far enough away from the source where your neutrino just flipped from detectable to indetectable, you detected too few of them, and you concluded there are not enough neutrinos. They were there, we can't see them.
Wow.
Right? And that was one of the things I said, okay, I was there when not literally in the room when that discovery was made, but that was the time when that discovery was made. And the other one, of course, is the expanding universe, right? Where we saw plots and said, we had seminar speakers said, oh, this, and that only works if the universe is expanding with an acceleration. Yeah. And the third thing I have to say, slightly outside my own area, gravity and all that, is exoplanets.
Right.
Right?
Yeah.
I remember, in school, in physics classes, we were talking, is there a possibility of other planets outside of our solar system?
Yeah.
And the argument was always theoretical. Oh, we have so many suns, we have so many galaxies, per galaxy there are so many stars, there got to be something, right? But actually seeing something that happened while I was studying physics, right? So it's never like this, this kind of fireworks going off and say, wow, right? Yeah. It's all these truths and all these understanding that kind of creeps in, and so you have this soft transition from ignorance to I understand, this is like that. And in retrospective, it's always, oh wow, that happened while I was alive, right?
It almost comes down to the waveform again. Like our lifespans are so short compared to the stuff that we're dealing with.
Yeah.
That in that tiny little up and down that we've got, we have to make these discoveries. Like we're not able to sit back and see things obviously at the scale of time.
But I think we found a very, very good way to extend our intellectual lifetime.
Yeah.
We write things down,
Yeah.
right? And we don't need Isaac Newton to be alive today to fly to the planet.
Yeah.
Right? We know how to do that because he wrote things down. And I mean, this is how science developed since like 5,000 years or something like that, even longer, when people started writing things down. And you didn't have to have the guy who knew how to do that alive and teach you.
Mm-hmm. It is extraordinary. I mean, it's one of the things that I talk about with my sort of kids' education stuff is just that it's like we've got the collective knowledge of the human race at our disposal.
Yeah.
Most of it on YouTube at this point. And all we have to do is just convince people to get excited enough to look into it. And that seems difficult,
Yeah, but this is an interesting problem, right? I mean, the big astronomy observatories run into that already now, where they are producing data at a rate and at a volume where it becomes a research effort to search that data.
Yeah.
Right? Because there's so much out there. I mean, if I put you in the Library of Congress and say, find the book about something, and all the classification is gone, and you have to go from book to book and say, no, that's not it, that's not it, right? Effectively, the knowledge isn't there anymore because you don't know where to look. Yeah. And we already have the problem now where some amount of data that we amass is so big that there are the first funding agencies out there, not the first. I mean, this is going on for a while, that hand out grants to look into the data already taken.
Already exists,
take new data, but just look into the old data. Is it already there?
Well, which is what Kepler was doing back in his day too, wasn't he? He was looking at existing data to make new discoveries.
Yeah, sure.
He just took the time to go through it.
Yeah, well, and yes, and people these days also have to take the time. Only the time is now measured in CPU cycles, right?
Right.
And not in how many candles you can burn in one day.
So true.
Kepler had the problem that there was no electric light.
Yeah,
right? So
that's another.
There you go.
That's another thing right there. I mean, the idea that we've got that more and more of our population is now able to work into the night thanks to cheap solar and batteries and that kind of stuff as well is going to make a difference as well. What what was I going to say? Oh, yes, machine learning. So, I mean, obviously, if you're dealing with like a fire hose of data all the time, like we all are at this point, I can only imagine what you guys are going through, given the amount of data that I get, and I'm just a fake TV guy. So, what are you using machine? I'm assuming this machine learning is coming into play. I won't use the term AI because it drives me nuts. But
both comes into play. But the joke is it's only called machine learning if it's from the machine learning valley in France. Otherwise, it's just linear regression and linear algebra. Okay, fine. That was the joke for the nerds.
Wow, somebody went deep on that one.
Machine learning is, and let's say machine learning or machine learning driven search routines are clearly the future, right? But I wouldn't even see that as a big paradigm shift or something like that. People always used computer to search databases. Right now, we might have a slightly better or efficient way to do that. Okay, fine, and we will use that. Same with artificial intelligence, right? Can we use things to predict where we need to point our telescopes based on a humongous amount of data that's already there, but a human brain cannot fathom in the time required to steer the telescope around? Probably. But I would see that as a tool evolving. At the moment, people are using machine learning techniques, but it's also still in a very much evolving field, right? It's not a mature thing where, like we would say, classical civil engineering, we know how to build bridges since the Romans, right?
Right.
So therefore, we now can concentrate on bridge architecture and other things. We are not there yet with machine learning or artificial intelligence. It's very much a co-evolving topic. But yeah, I'm sure there's the future. It's just one of those things where you stare at these things and say, I know it's the future. Now I need somebody to tell me how. Right?
Yeah, the
Because
way
sometimes it's difficult to find a way to, you have a new toy, right? And what can I do with it? Oh, it's fascinating, right? But
it's funny.
so I'm not a practitioner in neither machine learning nor artificial intelligence, right?
You haven't played with it at all?
Adventures in ChatGPT.
Yeah, I use it for programming a lot because I just find it's so good at that syntax based.
Yeah.
I have
colleagues that use that as well. I don't, but that's a matter of preference. And I also know colleagues people who use artificial intelligence and these generative AIs to give them ideas or first concepts of artwork or things like that. They say, oh yeah, do something like that, and say, oh yeah, that looks cool. Maybe I can do it a bit better. Yeah, sure. Yeah. Why not? Right.
It's amazing. I mean, it's definitely one of those things that I feel like not only can it just process the data, but it allows. It's that to me the appeal is always from the programming standpoint is that like a scientist who is not a computer scientist can use natural language to create a program specifically for their needs. I mean, that's what I like. Now, look, if you don't mind, we've got some questions. Are you ready for some questions?
Absolutely. Yeah.
All right. So we got Quackers29. You're going to love these names. Quackers29 says, is there an issue with laser interplanetary communication then? So if we have a base on Mars, is there an issue with laser interplanetary communication? Do we use lasers to communicate with Mars? Is that something that would happen, do you think?
We are not using, I don't know if we ever tried. I'm sure we don't do it routinely.
But the expansion of that laser would be...
Yeah, as you said, it boils down to the question: is it cheaper than normal radio transmission, right? And lasers have the advantage they can carry more data for the same amount of time, so to speak, whereas radio technology is much more mature. What I am sure is that we are using laser communication between satellites and from satellites to ground, certainly from low Earth orbit satellites. So anything up to 1,600 kilometers or something like that. And the issue there is, apart from the issue that you always have when you're talking to other planets, particularly to the outer ones, which Mars is one, right? It's further away than the Earth, that occasionally the sun gets in the way.
Right.
And then is when but this is also true for radio. So there are times of the year where we can't talk to our Martian orbiters because they are blocked by the sun. And then there are more technical issues where you say, the shorter the wavelength, the more prominent the scattering of the interplanetary dust is.
Right.
And so sometimes, and you know that from everyday experience, the sun is red when it sets because and it's redder and nicer the sunset if there's more dust in the atmosphere or water vapor. So it scatters away the blue light. So shorter wavelengths are scattered more significantly. So sometimes maybe a laser is not always the best option to communicate with interplanetary probes. The question really is there a technological upside? And the clear answer is yes, we can transmit more data.
Right.
And the interplanetary community, certainly the colleagues here who do have spacecraft flying to Mercury or to Jupiter, these things are far enough away that you seriously have to wonder about how to get the data back.
Yeah.
And, and their lasers would help, but we are certainly on the missions we have now flying to, like JUICE to Jupiter, Bepicolombo to Mercury. We do not have laser communication with Earth on board. We have laser-based instruments on board, but not for communication.
Right. Okay. So, Soma Proofed, or Broofed, I should say, says, actually, there's a question, would it be easier or cheaper to use radio waves instead of high-frequency waves, since you can build larger telescopes easier? So I guess this comes down to your question of why lasers over.
Funny that you asked that. We already have a detector like that.
Right.
Right. So let me expand on that a little bit. So you know that we have radio telescopes on the ground on the surface of the Earth, where that look at pulsars, faraway pulsars that
Right.
effectively are stars that emit radio signals at a very regular frequency.
Right.
And sometimes these frequencies is better known and more stable than our best atomic clocks.
Really?
So
Wow.
if we, it's very hard to disrupt a spinning neutron star. It's a lot of angular momentum.
Makes sense. Yeah, makes sense.
So if you observe enough of those and you time the arrival times of those pulses extremely carefully, you can imagine that if a gravitational wave passed through the path of those radio pulses from the pulsar to the Earth, they might arrive a little bit earlier or a little bit later.
Yeah.
And this is what the pulsar timing community is doing. There's a pulsar timing array and different, arrays around the world. Different radio telescopes collaborate with each other. And they last year, published the findings of their 10th year of operation or 9.5 year of operation or something like that, where for the first time the variation of the arrival times due to gravitational wave emission or presence of gravitational waves was clearly above the noise level. So yes, we are already using radio frequency, but what we are doing here is, for LISA, for example, we are detecting changes on the picometer range. Our wavelength is about a micron. So we are having 10 to the minus 5 of a wavelength or something like that we need to detect on something that is 2.5 million kilometers. Now, if you scale that up on radio, right, you could say, well, maybe I can have a radio wave, a microwave, that is going along this 2.5 million kilometers. But then to have the same precision, I need to slice the wavelength of the microwave, which is maybe instead of a micrometer, maybe 10 centimeters, making sure that 10 to the 5 times better. So I'm not having to slice that to 10 to the minus 5, to 10 to the minus 10, which means I need not 10 to the 5 times more power, but 10 to the 10 times more power, because the noise level of this, it goes with the square root. So yes, it's possible. It's not necessarily easier. Right? Plus, to be honest, on the civilian market, in the stuff we are dealing with here as scientists, we don't have big telescopes involved. Now, if you talk to the people who are listening into your cell phone conversations, they might have bigger telescopes and all bigger radio dishes, but they are kind of reluctant to give them to us.
Right.
And they're even more reluctant. They're actually already reluctant to admit that they have them.
Right.
Let alone giving it to us. So at the moment, technology-wise, it's much easier to use lasers.
Right.
And I say much easier. I mean, that has changed in the last 10 years, right? 10 years ago, when you talk to people, I want to put a laser into orbit, they looked at you and said, you must be insane.
Yeah.
They're not working for longer than 2 weeks.
Oh, even lasers. I mean, talk about things that have happened during
because this is one of the interesting challenges in designing for space. You have effects on ground that help you tremendously. Gravity helps you. It's not just a nuisance. Gravity allows convection to happen. And convection is an extremely nice way to get rid of heat.
Right.
If you are not having convection, you can gas fill your cell to say, well, I have conductive stuff and the gas and all that, yes, but you're lacking convection. So you're not actually, hot air doesn't rise anymore, right? So it's more difficult to get the temperature out. So in the beginning, that was a big problem because things on Earth effectively relied implicitly on a very efficient cooling mechanism.
Right.
That didn't work in space. And then there's material science where under gravity, believe it or not, some of the solars work slightly different or have a different property than under zero gravity. And so you had things shortening out that were not supposed to shorten out, and laser diodes dying that were not supposed to die. And so it took a while to get the technology right. Goes back to the thing is space is hard, particularly if you do technology for the first time, because you don't know what you don't know yet until you fly that stuff,
Yeah.
right?
Yeah.
And then you know, boy, do you know
Yeah.
what can go wrong, right?
Yeah. A lot can go wrong.
Yeah.
Oh,
Well,
wow.
this is also why things are so expensive, by the way, right? Because it takes a long time and a lot of testing and making sure that things work.
Well, and the redundancy, I'm sure, as well. Everything's got to cost 10 times as much because you need,
Yeah.
1,000 different solutions to everything, right? I mean,
Yeah.
how does funding work? Is it all government? Is it government and corporations as
We
well?
are not. No, we are. I mean, the European Space Agency, all of our space missions, okay, in the science domain at least, all of our space missions are completely government or publicly funded.
Right. So it's like NASA, same.
We
same
get
thing,
we get a bunch of money from our member states as a kind of yearly budget. But that's usually not enough to fly our missions. So typically we have member states, the member states of the European Space Agency that then show a certain interest into, I want our institutes to work on that particular part of the payload. I want them to work on the laser. I want to work them on the telescope, on the optical bench, whatever it is, right? And then they pay not directly to us, but they are paying their institutes to develop those things. So this is why it's very difficult when somebody asks me how much will the mission cost. I cannot at the moment because we are not at that stage yet. But eventually you could say what ESA paid for that.
Right.
But that's a fraction of what the mission really costs. And then you get into these weird and wonderful thing. We have 22, 23, 22, something like that member states. I hope nobody will kill me from my management for that. But we have a lot of member states with at least the same amount of number of different budgetary processes.
Right.
We say, this guy is, part of the overhead. We don't count his salary, but this guy is not, so we count his salary towards the cost of the mission.
Oh, wow.
And so that makes it intractable at the end. To be honest, it's pretty much impossible to tell you the cost of a mission to more than 1-digit precision.
Wow.
It sounds wild to say, how can that possibly be? Don't you know what you do with the money? Yes, we know what you do with the money, but what we don't know is how to precisely say this piece of money goes to the cost of the mission and that one doesn't. So it's difficult. But, for the amount of money we get, the agency gets, that's pretty clear. That's written down, and how much it costs us, that's also written down because we are dealing with industry and they really appreciate a contract where a number is in there, how much money they get. So we know that.
But Lisa is covered now. Like Lisa is covered, you're doing, Lisa
is covered exactly. In the sense is we don't have to fight for our budget anymore.
Right.
Unless something catastrophic happens.
Right.
We don't hope. I mean, things can always go wrong, but in principle we are covered, which means that we have the money to build 3 spacecraft, put it on a launcher and send it into orbit and operate it for 4 years.
And when does that happen? When are you planning on doing that?
If everything goes well, mid-30s, 2035, 2036, something like that. It's also, things where, of course, I could tell you that in the calendar we have, it's August 35, right? That's the maximum likelihood of all the simulations, right? It could also be October 35 or January 36. We will see. But it's about that time frame.
That's amazing. Well, congratulations on that then, at least. I mean, at least you got that seems like a big part of the battle.
That was a massive undertaking that, you're not getting this money just because you show up and say, look, that looks nice, give me the money. I mean, there's a lot of work in that.
And are there any particular member states who are interested in this? Did you find that there are certain countries that were more
This is this seems to be a mission that attracts more and more member states where they say, this is really interesting. Of course, you can imagine that the big ones that have large space industry to feed have a vested interest in our large missions, which Lisa is one of those. The big member states are typically Germany, France, Italy, UK, to a certain extent Spain,
Right.
so the big ones, and obviously, I mean, we have member states that are significantly smaller in economic power and also people. You know, Luxembourg, for it comes to mind, which is not exactly industrial powerhouse in Europe, and therefore they don't have a company or somebody who can do big things for LISA. But the nice thing about LISA is there's the hardware part where we have to build the spacecraft,
Right.
but there's also the data analysis part where the data that comes down needs to be processed and searched for gravitational waves. I mean,
Right.
it's not
Right.
that it comes with little stickers and saying, hi, I'm a gravitational wave. So we need to
Right.
do something with the data first.
Right.
And that is an effort where even relatively low level investment in hardware can help.
And
where
people, I guess, as
really
well, like just
exactly
brains.
the capital are the brains of the people, right? And the people. And so there we see also a lot more interest from the slightly less with member states with less economic power. Say, well, we can't invest 100 million in that mission, but we may be able to invest 1 million. And 1 million in hardware doesn't get you very far, but 1 million in data analysis and in people, that's a different story, right?
Right.
So
But you don't think of that, do you? I
so
mean,
we see interest. We see interest all over the place.
you sort of forget about the people side of it as well, don't you? There's such an appeal
No,
to the technology and
yes,
the
you should,
rockets and stuff.
but well, first of all, you should never forget about the people
No.
because without the people, it doesn't work.
Yeah. Yeah.
And yes, I mean, that's a fundamental truth, right? The technology is all nice and shiny, but you need people to put it together. But beyond that, I don't know if ESA ever did a formal breakdown there, but there are numbers floating around from NASA, and if we take them seriously, it suggests that 50 to 60% of the mission cost goes into people.
Yeah. I'm not surprised. Yeah. Not
The
surprised.
salary of people, right? I mean, I'm paid to work here, and
Right.
so are all of my colleagues and all the colleagues in industry who make that thing happen. It's not that we, I don't know what, build that thing out of the most expensive materials possible, and this is why it's so expensive. No, because it takes many, 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 many hours and many, 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 many people to actually build that thing. And that costs money, which is also good because these people use that money for other things, right? It's not burned. It's not that some of the money we burn, literally, the fuel for the rockets,
Right.
but
Right.
other money is not. It's not kind of completely lost to the world, I would say.
Right. It's investing in people as well.
Yeah.
Raj Luthra has a good question, and I might expand on this too. But how far can gravitational waves go? Like, what is? Let me add this, and I'll add this to it. You're talking about going back and seeing, the early universe. These things are propagating they must stop at some point, right? I mean, do they not? No, they're just.
No, they don't. I mean, this is a very good question. So the question is, how can they be? We're talking about stopping. How can they be absorbed, right? And so can you build for light? You can build a wall. And you shine light on the wall, and there's no light. So obviously the light got stopped, and it's absorbed in the wall and converted into heat and all that. Gravitational waves interact very, very little with matter. This is why it's so difficult to observe them. The upside is they're not stopped. They're not absorbed. So this is why we are typically saying, for these early black holes in the center of gravity, in the center of galaxies, when they have a certain size and give a certain signal, they cannot hide. We see them wherever they happen in the universe.
Oh, wow.
Right?
Okay.
Now, if you go a little bit further back, right, from the first galaxies, then you hit quite a bit further back, but then you hit what we call the cosmic microwave background, right? That's about 380,000 years after the Big Bang, something like that, where that's the first time. So this is what the COBE satellite WMAP Planck, these wonderful microwave background measurements. And where you hit the place, the time, not the place, the time when the universe became transparent, because all of a sudden the proton-electron plasma combined into neutral hydrogen atoms and others, right? And therefore, light didn't find that many scattering centers anymore. They didn't scatter off any free charge because there wasn't many free charge anymore. So all of a sudden, after that point, the universe became transparent and we see stars. Before that, it was a big fog, so to speak, right? So you couldn't see far. Now, that was a matter of density. Now, as I said, gravitational waves really don't care much about protons and electrons. They are not their thing, right? They are much too light, but you can go further back, right? So the question is, how far can you go back in time? You know, how many nanoseconds after the Big Bang, microseconds, I don't know what the answer is, do you have to go until the universe was so dense that it was intransparent for gravitational waves, in the sense that gravitational waves found so much mass that it scattered around and do the same thermalization, so which means going in all directions and all frequencies, from the like the cosmic microwave background. Now, this is the time where we talk about the gravitational wave background. And I'm not a cosmologist, so I can't tell you, you know, if it's microseconds, nanoseconds, or attoseconds after the Big Bang, but very, very quickly after the Big Bang. And LISA has a chance to see those things.
Wow.
So a chance depends on how loud the signal is, really, but and at which frequency range it happens. But you know, this would be say, well, this is where gravitational waves stopped, so to speak, because this is the density where they are absorbed. Now we turn that around because the universe expands from there. So this is where the primordial, what we call primordial gravitational waves or gravitational wave background were created. And then they are propagating effectively undisturbed through the universe.
So you would see a predictable pattern, or a pattern that you've predicted in
probably.
This. Right. I see.
I mean, as I said, I'm not a cosmologist, so if anybody of you guys out there listening from my cosmology group, don't kill me. But the thing is, the thing is, we know so little about this time of the universe. I mean, we have plenty of theories, I think, but we know very little about it. So, because we never measured. So I don't think that we can say we will see patterns. We are talking about spectra, so what is the frequency decomposition of those things?
Right.
How loud is it at different frequencies? That will give us an insight about the scale, how big it was, how the turbulence was at that time and all that. But this is as much as I'm prepared to talk about that without spewing complete nonsense, right?
Hasn't stopped a lot of other people, but it's so potentially you could turn this thing on and be like, wow, like literally there's things going on that we just completely unaware.
Not potentially. We will turn this thing on and it will have millions of signals.
Wow.
It's something we didn't talk about yet, but I'm talking about the things that happen out there at the edge of the universe, everywhere in the universe. But we have a galaxy directly in front of our doorstep, right? The Milky Way.
Yeah.
It has millions, and anywhere between 10 and 50 millions or so, depending on your favorite theory, how the Milky Way came together, of double star systems, and they are orbiting each other and spiraling in and emitting gravitational waves, and they are sitting bang in our frequency band, like around a few millihertz or so. And there are so many of those. I mean, imagine you're standing in the center, at the kickoff point at Wembley Stadium, or Rose Bowl, or whatever your reference point is, and you try to listen to somebody who talks to each other in the upper stands, you have no chance. There's so many of them, right? You're completely drowned out. But a precious few of them, like 1,000 or so, they are close enough. They are the players, they're the referee. They are close enough to you. You can listen to them, you can hear them. And you can even make out what they are saying because they're close enough. And these are thousands of, maybe 1,000 or so of them. And we call them our verification binaries because we know, for many of them, we know the frequency already and where they are in the sky because they also emit in radio frequency.
Right.
So we know what these guys are, and because they are not transient. So for us, that means they are on forever. That's not true. They're only on for a couple of million years, but that's good enough, right, for us. So they're effectively on forever, which means we switch the machine on. If it works, we see them. We know that, right?
And
then there's all the stuff that we don't know.
Is there more? And what through studying these gravitational waves? What is there any other data we could be bringing in? I mean, are we going to get we're going to get a better sense of their size, a better sense of their mass?
We get a better census. We get a better census of where they are. Remember, I mean, this is the thing, right? Optically, radio telescope, we can't really see through the center of the galaxy.
Yeah.
We see our half of the galaxy. The rest is obscured by dust and all that.
Yeah.
I think I mentioned the Horsehead Nebula.
Yeah.
That's dust. Right?
Yeah.
The reason why it's there and looks funny is because you can't see through. It's not that there are no stars. You can't just see through it. Gravitational waves don't care. They see the binaries in the whole galaxy. Depending, the galaxy is under some angle on the sky if you go into the ecliptic. So it's not, the Earth is not orbiting the sun in the same plane as the galaxy, right? It's inclined against that. So when LISA goes around, it sees the galaxy under different angles, and that gives a signal, and that tells you if the galaxy is, the binary star systems, if they're concentrated on a disk, or if they're more puffed up, or if they are completely distributed globally around the disk. They might be neutron star binaries that we can't see otherwise. Right? You say, well, if I had bright stars up there outside the galactic plane, you will certainly see them. Yes, of course, but they might be not bright. They might be white dwarfs, which are dim, neutron stars, which are very dim, right? Or they might even be black holes, which are ultimately dim.
Right.
So to
Yeah,
speak,
yeah,
right?
yeah,
You don't
yeah.
see them.
So we're able to see things that we'd never have a chance of seeing with existing.
I think we started out with that one, right? We see things that we never had a chance to see otherwise.
I just keep coming back to it. It's just such a neat concept. All right, Jim the Evo, wonderful Jim the Evo. Are there any alternative explanations for the readings which are thought to be gravitational waves? I mean, is there an alternative hypothesis that Oliver thinks would be interesting to explore?
Not really. I mean, you can always think about alternative theories of gravity and all that, but if you say, was it something else than gravitational waves? I think, and this was a serious question at the beginning, right, where the culture in the ground-based detecting is so that there are people who are injecting fake signals. Not because they want to trick people, but because they want to make sure that if people see something but haven't seen the fake signal, then something is fishy, right? You always should see the fake signal. So you can start thinking, went something wild there? Was there something going on? But I think there was one particular event that made it clear that we are seeing gravitational wave, and that was the detection of the gravitational waves on 17th August 2017, which was associated with a kilonova. Which means two neutron stars colliding and going through the full electromagnetic spectrum from hard gamma rays to deep infrared within a couple of weeks, I think, right? So while the thing, created all that radiation and then slowly cooled down, and it was coinciding with gravitational waves. And at that point, you start wondering, well, that would be a very weird coincidence if some noise object or something else hit my detector the same time this kilonova went up from the same direction. Yeah, okay. If somebody really, some evil mastermind fakes your data, you can do that, right?
Right.
But no, we are not. I mean, we are not that conspiracy-minded. We are skeptical, but not that much.
Right. It's, what does it say? Keep an open mind, but don't let your brains drop out.
Yes, indeed. But I mean, having said that, science is all about that, right? Maybe there's an alternative explanation for all these things. Well, all I can say, go ahead, try to find one, make sure it fits the data. It's not that we say, oh, no, this is that. No, it's much to the contrary. I think every scientist would be absolutely elated if he found a alternative, simpler explanation to something that has happened and was usually explained by something else, right? It's not the Grenton conspiracy where we say, no, this is now established theory. Far from it, right? It's a bunch of rabble-rousers, that these scientists. They want to find the whole theory, right?
It's funny. It's one of the things I both love and I'm so frustrated about the science side of stuff. Not as a scientist, is that it's like you want definitive answers, and you get them, but they're always like, but you know what I mean. There's always
Yeah, sure.
because of course you got to remain open to this stuff. So, all right. Piotronics says, could dark matter or dark energy change the way gravitational waves travel? And if so, how would scientists detect those effects?
Yes.
Feel free to answer. I'm going to just close the door because I've got a leaf blower outside.
Yeah. Okay, so let me start with the dark matter because that's probably the easier thing to understand. Dark matter is simply a word for stuff that acts gravitationally but can't be seen, hence dark, right? So we don't know what it is, but we know it's there because it affects how the dynamics of galaxies, it affects the light bending around galaxies. Now, gravitational waves, by and large, follow the same optical prescription as light, so to speak. So, gravitational waves go in a straight line unless there's a gravitational effect or gravitational acting mass around it. So it will be bent by matter concentration the same way as light will be bent. Not exactly the same way because it's a different frequency, but you get the picture. So one of the effects that makes it difficult to, for example, estimate the distance to faraway systems, even if we know their luminosities or internal brightness well enough, is an effect we call microlensing, where it's not the big thing where you go like, you peek through the bottle of a Coke, with the bottom of a Coke bottle, and you see everything terribly distorted, and you say, oh, that's a lens. It's more like, small fluctuations in the density of mass between us and them. And then if something moves a tiny little bit, it brightens up or dims down a little bit. This is what we call microlensing. That doesn't affect the position so much as the brightness. Gravitational waves suffer from that as well. So if we are saying we can determine the distance to gravitational wave sources very, very precisely because they are not absorbed, that's a little white lie because they are not absorbed, but they are bent, they are scattered by dark matter, and therefore you can see reflected in a sense, and you can then have a little bit of a error in determining the intrinsic gravitational wave brightness of these things. That happens. So yes, dark matter will affect gravitational waves the same essentially as it affects light. The expansion of the universe driven by dark energy and the accelerated expansion of the universe by dark energy, the same, because what this stuff does to light is what we call the gravitational redshift. So the wavelength of light is getting stretched, right? So things that are intrinsically blue appear red, and things that are intrinsically red appear infrared, which is, by the way, the reason why the things that we build that look into the far and distant universe, like JWST, looks in the infrared, because most of the stuff that comes from there is in the infrared. So gravitational waves will suffer from that the same. So when we are talking about the masses of systems that emit gravitational waves, we are typically a little bit sloppy, and we are just talking about the masses. What we should say is the gravitationally redshifted masses, which is a bit of a mouthful, hence we say masses. But it's understood that we can only ever detect the redshifted effect. So, which means that if the universe expands, then the way the universe expands affects our mass estimates of the things that are expanding with the universe, right? The black holes that are at the far edge and are moving away from us. So yes, it will affect both dark energy and dark matter will affect gravitational waves.
There's a question here that Quackers29 again has another question, which is what launch is going to be used to launch the LISA? How are you getting them up there, the satellites up there?
Ariane 6 is the current planning.
It is Ariane 6?
It's a European mission, European launcher. So yes, Ariane 6, certainly the mass budgets we have, where we say, we are limited to a certain amount of mass for the 3 satellites and a certain amount of size, are designed around the carrying capacity of an Ariane 6 and the size of the payload of the fairing. So this is the top of the rocket that is blown off at, once it's up there. But it needs to fit in there, right? So we are planning for an Ariane 6.
So not only do you have to design these things to do what you want them to do, you have to design them to be small enough to fit in the things to get it up there as well.
Small enough and light enough, yes.
Yeah, that's amazing.
You can't just. I mean, this is the perennial struggle of any space, system engineer and spacecraft engineer to make things as light as possible, yet as robust as possible. Yeah, it's difficult. Space is hard. We said that.
That's it. Oh yeah. Look, you just because we've got a lot of people who are interested in this stuff. I know I talk to a lot of kids about science and tech and stuff. What are your do you have any sort of advice for people who want to get into this kind of stuff? Are there any any sort of tricks? Any for going into to working on this kind of stuff and making these kind of discoveries and instruments and stuff?
Tricks? I don't think there are tricks. I think there's one fundamental quality that you have to have. You have to be curious. You have to be interested in that stuff, right? Don't do something that you find boring. That doesn't end well, right? Do things that you're interested in. And if you say, oh, I'm interested in science, but space science isn't for me, chemistry is cool, right? Yeah, fine, do chemistry. That's if this is what you're curious about with this. If you wake up in the morning, under the shower, in the evening, before you go to bed, and you start asking yourself, I wonder how that works.
Yeah.
Right? That's what you need. If you don't have that, nothing wrong with that, right? Maybe you're an artist and you are rather, I wonder how that looks if I paint it that way, or I wonder if I can reflect that scene, that emotion on a piece of paper. Also brilliant, right? But I think the key quality I see with successful scientists is this curiosity, right? What happens? I wonder how that works, right? And this is in all of us, I have the reputation of not being able to pass a button without pushing it, right? I wonder what happens if I do that.
Yeah, that's me. That's me. Yeah.
Yeah, exactly. But this is that. So this is not a trick, right? So this is something you have or you're interested in. So do it. In terms of what is the career path, where what topics do I have to select in school? Where do I have my AP classes, my IB things? Honestly, it doesn't matter. That matters less than you think. It matters in the sense that many universities these days sadly require you to have a certain grade to get in, right? Which is reality, and maybe not what we wish, but it is reality. And so there you go. But my key kind of experience when I started university was I was always very good in math and physics. And I thought I had it down. Let's just say the first 2 weeks of university went through all the math in school and beyond. And then we started.
Wow.
Right? Yeah. So the speed, the sheer breadth and depth of the topic there is so big that you will only get that if you keep curious, if you are interested, if it really motivates you. And it's, even if you had bad grades in school because you didn't like the physics teacher because he was weird, or the math teacher, she was a little bit strange, and fine, doesn't matter, right? If you're still interested, give it a try. And but after that, it's like every other profession. There are paths to success and there are paths to failure, and it's not yours to choose them effectively, right? A lot of that has to do with luck, a lot has to do with being at the right place at the right time. But as in every other kind of creative profession, I mean, you will know that, right? I'm sure you had a lot of roles that you didn't get because you weren't there when they were, exactly. But one thing I want to emphasize, I consider physics, math, chemistry, all these what we call STEM or topics, right, in English, they are highly creative jobs, highly creative professions. So don't think that, this is not the creative part. This is boring because you cannot create. Oh, you can. It's just a different thing of creating. It's not painting beautiful pictures with watercolors or something like that. And some of them can do that as well. I have colleagues here who are amazing, right? But it's about engaging your brain, thinking about new things, and express your creativity. And ultimately stay curious. Just be.
And you wake up every morning and go, woohoo, what do we got?
Yeah, these days I go up in the morning and I say, but
everything hurts.
My age. Exactly. But yes, I certainly have things where I think about, that's interesting. Let's look at that. A little bit of this. Oh, look, a squirrel problem.
Yeah.
You have that quite often.
Oh yeah.
Well, yeah, okay. I mean, there's not always the time and the place for that. Occasionally, you need to finish a job, but yeah, of course. I mean, I'm curious. This is one when Agni contacted me first a year ago, and then just recently about, do we want to do that? I said, hey, I never did that. Great, of course.
Yeah,
why not? See how that turns out, right?
Oh God, I'm so glad you did, and a huge thank you to Agna for making this happen too, because she's just been amazing with this. She's really pushed this forward, and it's such a great opportunity for me to actually learn some stuff while I'm while I'm online. So, speaking of this, I mean, I know I have a difficult time watching movies because I know how the magic works. Are you when you're reading science fiction, do you read science fiction at all? I
read science fiction. I mean, I really like science fiction.
You do.
I suspend my disbelief, right, when I'm reading about faster than light communication, some sort of warp drive or something like that.
Right.
I mean, that's fine. This is a mental vehicle to get the action going, and I can live with that, right? This is not a problem.
It doesn't ruin science fiction for you.
No, it doesn't. Where I do have difficulties are popular science books. I have to admit that. I rarely read them because I always have the feeling, I know the ones in the field where I'm working, where I know what's going on. I think, didn't quite get that right. And, clearly that guy didn't understand what's going on. And I transport that to the areas where I don't have a clue. So if I read a book about biochemistry or nanotechnology or things like that, I'm always wondering, if this guy has the same grasp of the concept as the guy who wrote that book, I'm not sure that I'm learning much from that one or the right things from that one. So I don't tend to read those popular science books. There are a couple of nice ones out there, and particularly when they are a little bit going to the history of people.
Yeah.
Sometimes people I happen to know or used to know. That is interesting, but more from the people angle than from the science angle, to be honest.
And is there anything coming up that you're really excited about? Any new areas, any new technologies that really have you that got the squirrel on?
I'm so deep in my own area, and that I kind of lost track of what else happens in the world of science.
Fair enough.
And everybody who works, on their PhD thesis or on a larger project will know the feeling that at some point you lose track of everything else. We talked about AI and machine learning. I think there's a lot of possibility towards that one. I'm not worried about some kind of singularity that the AI will all enslave us. I think that
seems a bit silly to me.
Far-fetched.
Yeah.
It's not impossible, but it's far-fetched. But I also think that eventually we will see more applications from things and proper and useful applications for things like quantum computing and all that. Not saying that they don't have applications now. People who know about that will probably say, oh, he has absolutely no clue what he's talking about. Yes, I have no clue what I'm talking about. But on the other hand, I've also not seen the giant simulation of the universe done in 2.5 seconds on a quantum computer, right?
Right.
So I think this is that might happen in the future, maybe not, doesn't really matter, but there is a path forward for all those technologies to help us in investigating nature. Right? Because that's what we are doing, right? There's the big riddle out there, and we try to get clues. And then when we found the clues, we found that the riddle became bigger. And we need to get more clues.
Yeah, it's
right?
like you find out you know less than you thought you knew. It's amazing.
Yeah. This is a funny thing, right? You do an experiment and think, after that, I know how that works. And you say, no, poo.
Yeah, it's so true. Any other areas or anything else you wanted to talk about? Anything you wanted to, anything you wanted to say to people before we wrap it up?
Just the usual. I mean, if you're interested in science, give it a go. And it's not the most glorious, thing. You will not be a show star, likely. You will not be kind of, being on the red carpet and all that. But there's this saying, if you do something that's fun, you're not working a single day of your life. Yeah, that part.
Yeah.
Right?
Oh, it's amazing. I find it, I'm so fascinated by this stuff and just so excited to be able to talk to you about this stuff, and thank you so much for giving up like almost 2 hours.
You're very welcome.
More than 2 hours, because we've spoken before as well.
Yeah.
I'll just double check, make sure there are no more questions. But Oliver, that was absolutely wonderful. What a joy. Yep, that's Agna. Agna sent all the questions. Anyone else got any last minute questions before I wrap up? No, I think we're good. Yes, thank you, everyone. Again, Oliver,
thank you for listening, guys.
People can find you on Twitter or X, whatever they call it now.
They can find me on Elon Musk's little
the Muskiverse.
The Muskiverse, yes. Simply, I usually go by my own name, Oliver Jennrich. So I'm not having a fancy handle there. On Twitter. I think I'm technically on Instagram, but you don't. I find much of me there.
Yeah, I feel like I'm of the age that Instagram is just a little lost.
No, it's not. I don't know if it's an age thing, but it is certainly a thing. Like, there are so many channels that you can provide with occasionally some content.
Yeah,
and you also need to get the feeling of the ecosystem, right? Things I say on Twitter or comment on Twitter are different from the things I do on Facebook. And Instagram, it would be probably even more different, and TikTok, and yet another thing, and yet another thing.
Yeah, so, that's it. There's just too many.
I have to admit that today has 24 hours and I have a job. Right?
That's it. Well, yeah, it's funny because I definitely I'm the same. There's one quick question here. Gippy G Gaming Lance has said, if Oliver were to extrapolate in his own field, what kind of neat science fiction device or ability could he see springing up as an end result of your own research? Is there any science fiction you could see coming out of gravitational waves? I mean, wow.
Yes, but somebody beat me to the task there.
Oh, really?
So yes, Alistair Reynolds probably as an author of science fiction.
Yeah.
Alistair used to work here 2 decades ago or so. As a scientist at the European Space Agency, and he has, I think it's him, has a novel about a civilization that did something dreadful, and therefore the powers that be enclosed them in a sphere, effectively, in their own local pocket universe, but they cannot stop gravitational waves from going through. So they use gravitational wave detector to figure out where they are. They can teleport in or out, but that's all they're allowed. So they don't know where they are in the universe, right? Because they always end up at the other end of the teleport channel. But if they build gravitational wave detectors, they can triangulate to the kind of gravitational wave pulsars. You can probably do that. It's a nice thing. We can use gravitational wave emitters for navigation. That's sure.
Yeah.
I mean, once we detect enough of them, it's possible. If that's a technical thing. I mean, usually I get the question, can we communicate with gravitational waves? Sure we can. Right?
You got a couple of big black holes ready to go.
Yeah. Exactly. The problem is that you need to move black holes around, and I'm sure I have some of my doubts. I think if you have a civilization that can move black holes and neutron stars around and will, they probably don't need gravitational waves to communicate.
Yeah.
Better means, right?
Slightly easier ways of communicating, I would imagine.
But I mean, on a more serious thing, also not really science fiction, but very much reality. The data analysis technologies we have, the way we analyze our data, also the things we learned about the behavior of accelerated masses, accelerometers, and they are used by industries that are typically interested in seismic measurements like oil, for example. Right? So we have people here who have spun off from their work in LISA Pathfinder into consulting with exploration companies, mineral and oil.
Really? Oh, that's interesting.
So there's this is there, but you know that's not sexy science fiction. That is
right.
Again,
But it's practical.
Work, but
it pays the bills.
Indeed.
Oh, that's great. Okay, so you don't happen to remember the name of the book, do you? Well, I'm sure someone will find it.
No. This is the funny thing. I'm not even sure. In my brain, I connect that with Alistair.
Yeah.
Yeah, I might be completely wrong. Right. Okay, I'm sorry. I know, and I even searched for that book because I think I read it on one of those e-reader devices, so I should be able to find it. Man.
No,
right? But I know that this book exists, so any one of the readers out there remembering that book and telling me that it was absolutely not by Alistair, it was by this other guy, fine. I mean, I misled you there. But
no, but if anyone's got the name of it, let us know. If there's anyone wants to do some OSINT on that. Again, Oliver, I'll wrap it up. I'll let you go. I'm sure you've got black holes to track and things. So thank you again. Thank you so much. Thank you to Agni.
You're so very welcome.
Thank you to Agni for making this happen as well.
And thank you to the patient audience.
Oh my God, no, that's great. People are like, thank you for the talk and thanks for listening and participating. Yeah, it's amazing. Everyone seems very, very happy, and as they should. So I will say I'll join you next week for another I'm with Genius, I hope. And in the meantime, I will say be brave, be kind.